Okay, good evening, everybody. So we know why we're here briefly is so that circle theorem will become something of a past, on the past. So we can understand circle theorem perfectly and not have any issue with it. So if we can dedicate a few minutes every night or every day for us to tackle all these theorems, theories, then we can achieve that goal. So please give me all your focus and attention for the few minutes we're going to use here daily, please. So circle theorem, of course, deals with a circle. So the major parts of what circle theorem bases its facts on are the facts of a circle. If I may ask you what a circle is, you may struggle to define, but we can say circle is, I don't know. Okay, circle is, there are points that have equal distances from a particular center. So let's assume we have a center, a dot at the center. Then you draw points away from that center, round the center, but have the same distance away from that center, all those points. So if you join all those points, you have a circle. So now, different theories are based on the parts, the various parts of this circle. And when we say various parts of the circle, you remember the parts of the circle we're talking about, segments. We're talking about tangents. We're talking about sectors. We're talking about the center, radius, diameter, chord. Good. Remember all these parts of a circle. It's very important. In fact, when we're going to analyze anything, we're going to be able to see if we can see the parts of a circle and know what they are, so we can relate them to the theorems, because the theorems are going to use the parts of those circles in explaining themselves or stating the theories. So the theories, they are just statements that will be able to prove significant results about the circle. So they'll be providing more information about the various parts of a circle. All right. And before we get to the theorems proper, let's define some terms. Like I already said in class, what is a subtended angle? A subtended angle is an angle made by something, an angle formed by something, an angle created by something. Now, what are the things that can cause it or can make an angle or a subtended angle? An arc can subtend an angle. A chord can subtend an angle. But all this, whether an arc or chord or whatever, is going to be from a given point. So an angle within a circle created by two chords that meet at a point will subtend an angle. They'll meet at a point on the circumference, of course. They will subtend an angle. So we are saying that in a circle, there will be various angles that can be formed by joining the endpoints of either two chords or two arcs or whatever. And when this happens, angles are subtended. All right. So you understand what it means, subtended angle. Now about an inscribed angle. That's like an angle made from points lying on the circle's circumference. Inscribe. When you say inscribe, if you think of something that is put inside another thing. So it's like an angle that is subtended at a point on the circle by two given points on the circle. So that's say it's formed by two chords that have a common endpoint on the circle. All right. Then a central angle is an angle whose vertex is the center O of a circle, and whose legs, that's the sides, are the radiuses, that's the radii, that are intersecting the circle in two distinct points. All right. I don't need to speak much of this English. Let's get to the theorems. So we'll start with this one, alternate segment theorem. So the angle between the tangent and the side of the triangle is equal to the opposite interior angle. Now I want you to take a look at this picture. We have a circle and we have a tangent under the circle, and we have chords. And listen, I'm stating out the properties of this angle we're looking at, or of this circle we're looking at. This circle we're looking at has an inscribed triangle. There's a triangle inside the circle. Now, just under the circle, you have a line that cuts the circumference of the circle, or touches the circumference of the circle. That line is called a tangent. So what are we seeing in that picture? We are seeing a tangent, and then we can't just call that triangle a triangle, though it's a triangle. But I'm seeing three chords. Can you see three chords with me? The first chord is the chord that has angle X and Y. Of course, both of them have angles X and Y. And then the other one, three of them have angles X and Y on them. But those three lines that form the triangle inside, look at them as though it's not a triangle. And you'll see three chords. So I have a tangent there, and I have three chords. Look at it very well. Remember I said when two chords meet, they're going to subtend an angle. So look at the chord on your right, by your right. The chord by your right goes from the tangent to a point on the circumference. The chord on your left touches the other chord on the tangent and goes to the left-hand side of the circumference. Then another chord joins the other two legs of the two chords that met at the tangents. So I have a tangent and three chords. These three chords meeting each other. So therefore they subtend three angles. Now, there is also an angle subtended between the tangent and the chords. Look at them very well. So I'll say again, what are the properties I found here? A tangent and three chords. Now, you know the straight line under the circle is what I'm calling the tangent. Looking at that tangent, you will see, and now let's look at the chords as a triangle now. You see a triangle and a tangent. By the right of that tangent, outside the triangle, you see angle x and y. Now we are saying that the angle between the tangent and the side of that triangle, that's y, and the x you are seeing here, down here, between the tangent and the side of the chord, that's the side of the triangle, is equal to the opposite interior angle to each or any of the angles subtended between the tangent and the chord. Now let's look at y alone. Y is painted red. The y down here subtended between the tangent and the side of this triangle. That y is equal to the angle that is interior, the interior angle in the triangle, but is opposite this y we are looking at. Look at it very well. That's why it's also labeled y. This tangent, or the angle subtended between the tangent and this side of the triangle, the y just down here, is opposite the other y we are seeing, but the other y is inside the triangle. That one inside the triangle is the interior angle, and that interior angle is opposite this angle between the tangent and the side of the triangle. Now, listening to what I've said, I'm going to read this theorem again. That the angle between the tangent and the side of the triangle, that's the angle y here, down here, is equal to what? The opposite interior angle of that triangle you're seeing there. So you see, y is equal to the other y that is inside there. You can also go the same way with x. Turn to the left hand side of this tangent, just adjacent y. You'll see that x will be equal to the interior angle x the other way. So it's clearly written there, x equals to x and y equals to x, or y equals to y. Correct. This figure has a tangent DE. Looking at it, you see DE meets the circle at A. So you see line DAE starts from D and ends at E, so we call it DE. But at the point where it touches the circle, which makes that line DE a tangent, is point A. So we have tangent DE, and we have chords here. But the most important chord there is AC, because it's the chord that produces the angle that we can use as reference right now. So we have a tangent, a chord. I'm calling the most important chord out now. A chord, and we have angle CAE. So three important things we have there. It's tangent DE, chord AC, and angle CAE. That's what is going to help us to solve that question. Now, once you are able to list out those properties, then your mind takes you to a theorem that has these properties in it. What theorem has tangent, chord in it? So you quickly go to the theorem we just did today. That's the alternate segment theorem, which states that if there is an angle formed between the tangent and the side of an inscribed triangle, then that angle formed between that tangent and the side of the inscribed triangle will be equal to the opposite interior angle of that triangle. So we look at that question. The angle formed between the tangent and the side of the inscribed triangle is 82 degrees. And we said the rule says that it should be equal to an angle that is opposite that angle 82 and also inside the inscribed triangle, which is ABC. That's theta. So we can easily say from that rule that ABC, that's theta, is equal to 82 degrees. Why? Because angle, or because they are alternate, what we call it, alternate segment angles. Do you understand? So today we are looking at another rule. The angle at the center is twice the angle on the circumference. Now, I know this particular theory is common and easy, but I want you to know that there are ways it can be twisted, and then your brain is all bad if you're not grounded in it. But before then, let's also consider the properties of a circle that should activate this rule. And when we see a equation, what properties should we be looking out for to know that is this rule we are applying? So in this theory, we're dealing with the center as the most important part of the circle, the circumference, and the chord. Three things: the center, the circumference, and the chord. So we're looking at where's the center of the circle, And then what is the angle? Where is the angle? Is there any angle at the center or formed or subtended at the center of that circle? If there is, okay, then it's going to be chords that form the angle at the center. Does it touch the circumference? If it touches the circumference, then we're looking out for what is the angle that is formed on that circumference by the chords that forms or that emanates from the center of that circle. So now the center of the circle is just the point that locates the middle of that circle, and the circumference is the distance around the circle. I mean, right around the center, distance around the edge of the circle. And a chord, of course, is a straight line that meets the circumference in two places. Okay, and you should also know that the longest chord in a circle is the diameter. So your chord keeps cutting off until it reaches the middle, and which is the longest, and you call that the diameter, right? Now, remember I said that there are ways that the angles can be twisted, and then it becomes difficult to locate. Now, let's take this picture I just sent, for instance. Now, looking at the circle on the right, you see a normal circle with a center, which is twice the angle formed at DAB or BAD. Now, that's the theorem we're talking about. But I want you to pay a closer look at the chords that emanate from the center. 4 chords. Now, these 4 chords have different colors because of this explanation I'm going to make. Look at the green chord, look at the purple chord, look at the pink chord, and the blue chord. The green chord is from C to D, the purple from C to B, the pink from D to A, and the blue from D to A. Now, we're looking at the center and angle A. I'm still looking at the one on the right, not the left yet. So from our rule, angle A, we're paying attention to only angle A right now, should be divided by 2 of angle C, because angle C should be 2 times what angle A is. So let's say angle A is 40, then angle C, at the center, should be 80 degrees, 2 times that. Now go to the picture on the left, and you see these 4 colors of the chords are twisted. So the green chord came out, hit the circumference just like normal on the right, left, same as the right hand side picture. The purple did the same, hit the circumference. Now instead of this thing to form its normal shape it formed on the right hand side, it was twisted to form an angle on a different area, not to complete what looks like the kite. So in such a way, A is then transferred to another place. Angle A still remains divided by 2 of what angle C is. You will understand better when I start sending you pictures to give me answers. But all I'm saying is, whether the angle is twisted or not, if there is a link to show that the chords emanate from the center and touches the circumference to form angles on the circumference, the angle at the circumference is going to give you divided by 2 of the angle at the center. Or we say the angle at the center is going to be 2 times the angle that is formed on the circumference. If the chords emanate from the center but doesn't touch the circumference, doesn't form an angle on the circumference, then the angle formed on the circumference cannot be determined. So there is no way you can solve that question. So all I'm saying right now is take note of the center. Is there an angle formed at the center? Good. The chords leading out of the angle formed by the center, does it touch the circumference? And if it touches the circumference, the angle formed on that circumference, the angles formed will be 2 times, or will be divided by 2 of the angle at the center. So, question 1, we have 84 degrees that forms part of the center of that circle, and inside the triangle. Now, 84 degrees is just one side of the circle, not the one that's not the angle that is 2 times y. What I'm saying is, the angle at the point in that circle sum up to 360. 84 plus something else should sum up to 360 to make that center complete. The part labeled O is the part that is 2 times y. So we have to find that part first by saying 360 minus 84. That gives us 176, 276. So we now have 276, which is in the right position to be 2 times y. So 276 degree equals to 2 times, or y, yes, it's 2 times y. So to find y, we say 276 divided by 2, which will give us 138. So y is 138 if I'm not calculating wrongly. Now for question 2, we have angles that are named. There are no values. We're going to use models to try to solve this. That's to say, y is the rule we learned yesterday. That is, angle at the center is twice the angle on the circumference. Y works with that theorem with B. Yx works with that same theorem with A. So what do? It's very important to first find the center. Okay? So if we have y, then x is 360 minus y, isn't it? So we say x equals to 360 minus y. We have found our x. And we can say y equals to 360 minus x. We found our y. So how then can we find b? B is y divided by 2. A is x divided by 2. As simple as that. No values, but come up with a way of explaining. So in such a way that if there were values, that would give us a correct answer. In question 3, we have an isosceles triangle inside the inscribed triangle, which makes it interesting. That's to say, we have in an isosceles triangle that the base angles are equal. That's angle CB, OBA and OAB should be equal. And we have one of those angles at B to be 40. So because base angles should be equal and one of the base angles is 40, then the angle at A should be 42. So if we have 40 and 40, what do we need to complete the sum of angles in the triangle, which is 180? We just say 180 minus 40 plus 40, which is 80. 180 minus 80, and we discover that this tip of the isosceles triangle is 100. So if the tip of the isosceles triangle is 100, it forms the theorem we studied yesterday. The angle at the center is twice the angle on the circumference. So that means x is 100 divided by 2, which becomes 50 degrees. And then finally, in this case, we're asked in the following: the red line is a tangent. Find A and B. And you have to give reasons, very importantly. So that tangent is very important. Remember our rule of tangents, that if an angle is formed between the tangent and the side of a triangle, then the side of the inscribed triangle, then the angle formed between the side of the inscribed triangle and is equal to the opposite interior angle of that triangle. Now make no mistake, the triangle we should be looking at is the triangle that is by the right. It's not labeled well. I mean, we need to see a label for the point that marks the tangent and the other points on the other circumferences, or circumference, the other points on the circumference. But since we don't have that, we're going to be very reasonable in arranging this. Remember, the tangent is formed between a straight line, a chord, and the tangent. It's the angle is formed. The angle on the tangent is formed between a chord and the tangent. So look away from this triangle that leads to the center and look at the chord. Then you will see a triangle on the right hand side of that chord. So 115 should be equal to A. Now, I found A equals to 115 degrees. The reason is that A is the opposite interior angle of the angle formed between the tangent and the side of an inscribed triangle. Now, let's come back to 115. Look at the tangent, which is a straight line. So it forms a straight line angle, which should be 180. So you look at 115, and you see the space between the chord and the right hand side of the tangent. 180 minus 115 should give us that space remaining. If we calculate that, we'll have 65 degrees. So 65 degrees goes to the right hand side of this tangent. And if 65 degree goes to the right hand side of that tangent, then it should be equal to the opposite interior angle of a triangle, the one that leads to the center now. And now, if we look at that one that leads to the center, we see that there is a space there. So that space is 65. And that space at 65 is to complete that circle. Angle at a point is 360. So we can then find B by saying 360 minus that 65, which should give us 295 degrees. So B is 295 degrees. So today, quickly, we're going to look at the role of angles in the same tangent, or segment, sorry. Angles in the same segment. And the rule says that angles in the same segment are equal. You can see that in the picture above. Now I want to dive deep into it, so pay good attention. So as usual, let's discuss first the key parts of a circle. What should you look out for the rule of today when you're looking at a circle? Now you see that the picture I sent now, this circle is divided into two by a chord. There is a chord that divides the circle into two parts. The smaller part is the minor segment, and the bigger part is the major segment. Now, the circumference of the circle that bounds the major segment is called the major arc, while the circumference that bounds the minor segment is the minor arc. And you see all of these are in different colors, so you understand clearly. As the major segment is pink in color, and the major arc is green, a green line around the major segment. The minor segment is yellow in color, and the minor arc is a deep pink color. The major segment was a baby pink, light pink color. Now, the chord is blue in color. So that when you look at it, you see there are different properties. But what are you to look out for this rule to be active? You need to see a chord dividing the circle into the minor segment and the major segment. And when that happens, you already know that the circumference surrounding or bounding the major segment is the major arc, and the minor arc is that bounds the minor segment. Let me just remind you what a chord is. A chord is a straight line that meets the circumference in two places, that blue line you are seeing. And we said before that the longest chord in a circle is the diameter. Now, the major segment there you are seeing is the larger segment of a circle that is enclosed by a chord and the major arc. The minor segment is just a smaller part of the circle, which is cut by a chord and the minor arc. But what is an arc? It's a part of the circumference. The major arc is longer and minor arc is smaller. Alright, we already discussed the other time what we mean by what a subtended angle is. But let me say it again for the people that just joined in today. For angle, we say an angle is subtended or created or formed when two chords meet at a point on the circumference. Okay, so just as a definition, but we'll get to see all of that. Now, in this diagram, you discover that BD is a chord. Remember, we discussed this already. BD is a chord, and BD is that chord that divides this circle into the two segments. The segment that contains this triangle BAD and BCD is the major segment, and this other segment down below BD is the minor segment. Doesn't contain any angles yet. So I'm saying BD is the chord that divides the circle into the major and the minor segment. So now these 2 points A and C that touches the circumference, they are, and of course you see that they are joined by the other 2 points, that's B and D. So we can say that the angle DAB, that's theta at A there, is the same as angle BCD, as a theta at C. Now this is the same for any point that is placed on the major arc. So that means the angles formed on the circumference or in the same segments are equal. What I'm saying is, you see, BD is the base, the chord that carries these two triangles that sit that are in the same segment, the major segment. The first angle BAD, I want to call that the first, is still controlled by B and D. The second angle BCD is still controlled by B and D, so they have a common base, which is the chord. Now, take note of what is important in this with these two triangles inside the same segment. These two triangles are joined by the lines AB and CD. What I mean is the green line and the blue line. The green line and the blue line lead these two angles to the same base. If they don't emanate like this, those angles at the circumference wouldn't be equal. This is what I'm saying. Let's assume the purple line from B hits C as it is, but the green line didn't come to D. Maybe it came to somewhere between A and D. The angle at that C wouldn't be equal to the angle at A. So you see how important that line that joins C with D is. Also, let's say D hit A like it is in the picture. That's the pink line. If the blue line AB maybe didn't go to B, it went to C, the angle at A wouldn't be the same as that in C right now. So things to note: the chord, and then the angles formed in a particular segment, and then this line that joins these angles are important to note. Now, the question you would be thinking of is, okay, we've talked about these major segments, that these angles are formed in major segments. What if there is an angle on the minor segments? Yes. If there is any point that is placed on the minor arc, okay, that's the minor segment, this is called DB. There are angles that are taken to meet the minor arc, and the angles formed on the minor arc would still be the same. Okay, like not the same with the one in the major segment, but all the angles formed in the minor arc from that same common base would be the same. All right, so the same thing for the major segment would happen in the minor segment. Okay, now there would be some questions that will come up to test how smart or how equipped you are in this theory. If you look at this picture, DC has not been joined. So DC is still a chord, but it's imaginary. That is, you know that looking at D and C, it forms a common base for angle CAD and angle CBD. So you will still regard DC as a chord, a common base. So even if there is no chord that tends to divide this circle into two segments, DC serves that purpose. Because if you just silently or with your mind put in a line there, you will see it come out clearly. So what it means is that in this question, angle CBD is still equal to CAD. That is to say, the theta at A is 47. I hope you understand. So this one is easy. So looking at it, looks like it's not easy, but it's very easy. What we're looking for is the theta at B. That's we're looking at DBA or ABD. That angular theta at B is what we're asked to find. Now you have 79 degrees at the intersection of the two triangles. That is to say that angle DEC is 79 degrees, and you see that it's vertically opposite to angle DEB. So that makes DEB 79 degrees too. So we're looking at the angle AEB, that triangle that has the theta, we already have one value, 79 degree, which comes from the vertically opposite angle BEC. So we have 79 degree inside and I'm waiting. And then the other two sides we have theta, and then the other side which we want to form now. Now, if the chord that divides this circle into two segments is on BC, that's this base we're looking at BC, then the angle at D should be equal to the angle at A. So the 44 we're seeing in D, we can also transfer that to A to be 44. That makes us have in triangle AEB, we have 79 degrees and 44 degrees. If we add those two together, 79 plus 44, we have 123 degrees. So we can say 180 minus 123 degrees to give us 57 degrees for theta at B. It was as easy as that. Do you understand that? So today's focus is in front of us. Opposite angles in a cyclic quadrilateral. That's the rule we're considering tonight. The opposite angles in a cyclic quadrilateral. And the rule says that opposite angles in a cyclic quadrilateral add up to 180 degrees. And let's see how to break that down. So what is a cyclic quadrilateral? A cyclic quadrilateral is not a quadrilateral that looks like it's a circle. Because as the name implies, you'll be thinking a quadrilateral that is cyclic in nature is a cyclic quadrilateral. No. A cyclic quadrilateral is first of all a quadrilateral. That means it's a four-sided shape. Four-sided shapes are called quadrilaterals. So a cyclic quadrilateral is a four-sided shape that is inscribed into a cycle. That is, you have a four-sided shape in a cycle. Inside a cycle, that's meaning inscribed. So that means a cyclic quadrilateral is a quadrilateral inside a cycle. Alright? But what makes this quadrilateral inside a circle qualified to be called a cyclic quadrilateral is that each of the points, the sharp edges of this quadrilateral, should touch the circumference of the circle. If the points that form the sharp corners of the quadrilateral do not touch the circumference, then that is not a cyclic quadrilateral. So what I'm trying to say is that each vertex of the quadrilateral should lie on the circumference of the circle, and then the chords should connect them. Being a quadrilateral means that it will have four chords. So look out for the following properties. The chords are the chords 4 as the lines that intersect or touches the circumference. And therefore, then they're going to form four-sided objects inside that quadrilateral or inside that circle. So we need four chords, and these four chords should connect at the circumference. Alright? So the opposite angles of this kind of quadrilateral, if that's a quadrilateral inside a circle, the angle that is opposite another angle will have a total of 180 degrees. As if you add both of those opposite angles, it should sum up to 180 degrees. As you can say, the opposite angles of a cyclic quadrilateral sum up to 180 degrees. Or you can put the rule this way: the opposite angles of a cyclic quadrilateral are supplementary to one another. Because supplementary angles some add up to 180 degrees. So we can say that the opposite angles of a cyclic quadrilateral are supplementary to one another. Let's use this photo I just sent to explain better. Now you discover that the circle on the left has a quadrilateral inside, or let's say it has a shape inside. So we want to follow the properties. So I said let's first ask ourselves, does this shape inside have four lines? That's four chords. Yes, it has four chords: the blue, the purple, the green, and the pink. The next question would be, does each of these chords touch the circumference of the circle? Yes, the blue line AB touch the circumference, the pink line AD touch the circumference, the green line DC touch the circumference, and the purple line BC touches the circumference. So therefore the shape inside there is a quadrilateral. So I've explained it now. Looking at the one on the right, green, purple, blue, pink lines, four chords, and each of those chords touch the circumference. So the shape there is also a quadrilateral. So these two shapes inside these two circles qualify to be called cyclic quadrilaterals. Let's go back to the one on the left now. The angle D is opposite the angle B, and the angle C is opposite the angle A, or the one on the left hand side now. So because they qualify to be called cyclic quadrilaterals, then angle D, which is opposite B, should add up to 180 degrees. That is, if B is X, then D should be 180 minus X. The same goes for A and C. If A is Y, then C should be 180 minus Y. Go to the one on the right. Angle A is opposite angle C. Angle B is opposite angle D. So the same thing. Angle C should be should sum up to 180 with angle A, and angle D, when added with angle B, should sum up to 180 degrees. So if angle C, or if angle A is X, then angle C has to be 180 minus X. And if angle D is Y, then angle B will be 180 minus Y. Now a quick one. I want to add this, that the sum of angles inside any quadrilateral is 360 degrees. That is, if you look at the left hand side, you have quadrilateral ABCD. If you want to add angle A plus angle B plus angle C plus angle D together, everything inside that quadrilateral should sum up to 360 degrees. The same with the one by the right hand side. Whether the quadrilateral is inside the circle, that's whether it is a cyclic quadrilateral or a quadrilateral just on its own, sum of angles inside the quadrilateral should be 360 degrees. Now we want to solve this, but I want to point out something. The people setting questions to you, whoever wants to set a question, whether it be any math question, any question, don't want you to easily crack and get the answer. So they will try to confuse you. Take for instance, look at this picture. We are told that quadrilateral ABCD is a cyclic quadrilateral. Calculate BAD. If you look at BAD, that's where its point is put theta. So first of all, we analyze the properties and see if it's qualified to even call a cyclic quadrilateral. We have 4 chords, and each of these chords touch the circumference, so it's qualified. So let's identify the opposite angles. Angle A is opposite angle C. Angle B is opposite angle D. Now, but you discover that this question, they gave you angle B and angle C as known angles. Clearly, you need to just find BAD, and BAD is one opposite 105. So your answer is just 105 degrees. The question you'll be asking yourself is, what is 138 doing there? They can give you unnecessary information to try and topple you, confuse you, so you won't get the answer. So once you are sure that your step is correct and that your answer is correct, don't confuse yourself with the added information in the question. Not just math, any question. Alright? So here we've solved and we said that DAB or VAD is 180 minus 105. It's not 105, 180 degrees minus 105 degrees, which is 75 degrees. That's for BAD. Remember, it's not 105 degrees because we said opposite angles in a cyclic quadrilateral are supplementary, as they add up to 180 degrees. So if C, which is opposite A, is 105, then A, which is opposite C, will be 180 minus 105, which is 75 degrees. Now, looking at this other one, ABCD is a cyclic quadrilateral with center O. Calculate the size of angle ABC. Now, you can ask yourself the questions you want to ask to confirm if it's a cyclic quadrilateral. It has 4 chords, and the 4 chords touch the circumference. So it's a cyclic quadrilateral. Let's identify the opposite angles. D is opposite B, and A is opposite C. Now, but we have a diameter, which forms a circumference. So we can also apply the rule of angles on a diameter, that's angle on the circumference, from 90 degrees. So you see that DAB is 90 degrees and DBC is 90 degrees. But let's look away from that and go to what we want to find, ABC. Now, we discover that angle D totally is 64 plus 35, which is 99. So ABC, the angle that is opposite B that we are looking for, at opposite theta, is 99 degrees. So of course, you know, what would B, that's theta B, would be 180 minus the 99 there, which gives us 81 degrees. So ABC equals to 81 degrees. I hope we understand. Now, before I give you classwork, look at example 3. ABCD is a cyclic quadrilateral inside the circle with center O. BOC, that's angle BOC, is in the inscribed angle of chord BC. So I have to calculate the size of angle ADC. So we have 4 chords touching the circumferences to form a cyclic quadrilateral. But on the chord BC, we have a triangle. Now remember that a triangle that has a common base as a chord, the chord of a circle, and meets at the center of the circle is going to be an isosceles triangle. So that means angle COB or triangle COB is an isosceles triangle. As the triangle on chord BC is isosceles. And if it's isosceles, it means that the 2 base angles are going to be equal. So the work becomes easy. Now, since we have 100 as the major angle, then what is remaining to complete 180 degree is 80 degrees. And then we divide that 80 into 2 and spread it as the base angles of the isosceles triangle. So that's 40, 40 each for C and B. Now, if we do so, then angle B there becomes 48 plus the 40 we just added. 48 plus 40 is 88. Now we have completed ABC to have 88 degrees, and angle ABC is opposite angle ADC that we are looking for. So since that's 88 degrees for ABC, then ADC will be 180 degrees minus 88 degrees, which is 92 degrees. That's the answer for theta as ABC. So tonight we are dealing with angles in a semicircle. Angles in a semicircle. Now I want you to look at this rule as a two-way rule. A two-way rule. Now, how do you create a semicircle? If you have a diameter, the diameter divides a circle into two parts. Those two parts are semicircles. So imagine that you have a diameter, or just one diameter. That diameter will divide the circle into two parts. Each part is a semicircle. Now, angles in a semicircle are created when you join the two ends of that diameter, to one point on the circumference of that semicircle. Okay, I should call it circumference again. Okay, arc. I'll still call it circumference. So you have a diameter, and the diameter passes through the center of a circle and touches 2 points, the two ends of a circle, to totally cut the circle into two parts. Now I'm saying, look at that diameter you're putting in your head now, and then draw two chords from the two ends of the diameter to meet another point on the circumference of the semicircle you just created. Then you formed a 90 degree on that point you just created. That's how angles are formed in a semicircle. Alright, so I'm saying angles in a semicircle are created when you join two ends of a diameter to one point on the circumference of the semicircle. Alright, so let's use this picture as focus. Now I've already explained how you form an angle on a semicircle. So you look at the green line, the green chord, or the green line, which is our diameter. You divide the circle into two parts. Now this part that the triangle ABC is in is one semicircle, and the other one that is empty is another semicircle. Now we're forming an angle inside this semicircle by drawing two chords from the ends of the green line, from the ends of the diameter, to meet a point, any point, so C, on the circumference of this other semicircle. And then we see that we formed a 90 degree angle on that point on the circumference. That's how angles are created in a semicircle. Right? Now it's not just one diagram, like it's not just one angle that can be formed here. Like you see in the former picture we used, you discover that you can form 2, 3, 4 angles on that circumference, as long as the chords are emanating from the two ends of the semicircle and touches just one point each on the circumference of the semicircle. Then 90 degree will be formed on that circumference. Okay, now I want you to think of this. If 90 degree is formed on the point C of that triangle ABC, sum of angles in a triangle is 180 degrees. Then total of the angles in A and B should be 90 degrees, right? Good. So this rule we just did right now. We're saying that angles in a semicircle are 90 degrees. As the angle formed on a semicircle will be 90 degrees. Remember I said you should see this rule as a two-way rule. One is that angle in a semicircle is 90 degrees. Angle C is 90 degrees. But angle A and B sum up to 90 degrees. So that will become angles on a diameter sum up to 90 degrees. That is, if we add up the angles formed on the diameter, not on the semicircle now, on the diameter of that semicircle, angle at A and angle at B should sum up to 90 degrees, because C is already 90, and sum of angles in a triangle is 90. It's 180 degrees, sorry. So I'm saying it again. The first rule, let's say two-way rule. The first is that angle in a semicircle, an angle formed in a semicircle will be 90 degrees. Then which also means that the sum of angles formed on the diameter that forms this angle 90 on the semicircle will sum up to 90 degrees also. So I can say sum of angles in a diameter is 90 degrees, which entails that the angle formed on the semicircle is 90 degrees. Now, if we look at these two shapes, the one on the left is the full version. The one on the right is just the diameter AB is cut off to divide the circle on the left into two sides, and one side is taken to the right. Now, I want you to look at the one on the left. We have a quadrilateral A, B, C, and the faded part here, which I can call D. No, A, C, B, D. Now, the diameter AB divides that quadrilateral into two parts. But look away from the quadrilateral, you see that the triangle is formed in triangle ABC is formed, and triangle ABC has C as the 90 degree because it's formed in the semicircle. It's an angle formed from a common diameter, and the point is on the circumference, so it forms a 90 degree there. Okay, so but you can see technically that if you divide a rectangle by a diagonal, and the diagonal forms the diameter of the circle, then you're going to have two right angles on either side of the semicircle you just created. So what are the key parts of a circle we are looking out for when we are dealing with this theorem of angles formed in a semicircle? The circle itself must be there, of course, so that's not the problem. But the diameter is the major part of the circle, because the diameter is what's going to divide the circle into semicircle, and our rule is about semicircle. So the diameter, should look out for a diameter, and then Of course, the center of the circle is also very important because the diameter must pass through the center. So you can see a line and you think that's the diameter, and if you see the center at another point, then you did not see the diameter. So note the diameter and the center must be, note that the diameter passes through the center. So I said you're looking for the diameter, the center, and then the chords. And when you're looking for the chord, you're thinking of the chord should touch the diameters at both ends, and then the other, where the two chords meet, should be on the circumference or the arc of the semicircle. All right. So the diameter, the center, and chord are the key parts we are expecting in this theorem. You still know what the diameter is. The diameter is the line that divides the center in the circle into two parts. The diameter is the line that passes through the center and touches the circumference of the circle on the two ends. Right. So if you've cut like in the shape on the right hand side of this picture is a semicircle. So if you're looking at a semicircle, this straight line is the diameter. A circle doesn't have a straight line, but in a semicircle has a straight line. So the straight line is the diameter. Then you also know that a chord is a straight line that meets the circumference in two places. So we can call a diameter a chord, but diameter has a special name. Diameter is a chord because a chord is any line that meets the circumference of the circle in two places. But the diameter is a special chord because the diameter can only be one and is the longest chord in a circle. Okay? So a semicircle is half of a circle. Just remember what a subtended angle is, a created angle when two chords intersect or meet at a point. Alright? Now we can see in the question that we have a circle and we have a diameter AB. How do I know it's a diameter? It passes through the center and touches the circumference at A and B. So clearly it has divided this circle into two parts. One part which is up is empty. The other part which is down contains the triangle we are looking at. And because these conditions have been met, conditions of a diameter is formed to divide the semicircle into two. And then there are two chords, chord AC and chord BC, from the two ends of the diameter and meet at the semicircle at point C. Then I know that this point C is 90 degrees from the rule of angle formed in a semicircle. So I know that ACB is 90 degrees, and we are given ABC as 67 degrees. And I know sum of angles in a triangle is 180 degrees. And I would just say that 90 plus 67, which is equal to 157. And I say that theta will be 180 minus 157, which is equal to 23 degrees. So theta, which is BAC, equals to 23 degrees. Now this one, we are asked to find ACB. ACB, that's marked theta. Now we look out for what makes this rule, what qualifies this whole diagram to the rule of angles in a semicircle. And we see a diameter that divides the circle into two parts. The first part contains triangle ABC, the other semicircle contains triangle ACD. Now we are given that triangle ACD is isosceles. If triangle ACD is isosceles, then the base angles A and C of ACD are equal. So if we can find ADC, that's the tip of the triangle, that's a D, then we can unlock this equation. Now let's see. Now the semicircle that triangle ACD is in shows us that D is 90 degrees because it's angle formed in a semicircle. Now if D is 90 degrees, then sum of angles in the diameter AC of ACD is 90. So that means we have 45 at A and C of triangle ACD. Okay. Now if we have 45 here, that means we can find angle A. The whole of angle A is 107. We can find the angle A of ABC as 107 minus 45 that we just found here. And that would be 62. So that means angle BAC, that's the A here for ABC, is 62 degrees. And if we found that that's 62 degrees, we also remember that triangle ABC is angle on a semicircle up now. That makes B 90 degrees. So we say 90 plus 62 we just found for A, and we have 152. Then to find theta we say 180 minus 152, and we have that triangle BAC or ACB we're asked to find is 28 degrees. Do you understand? So yeah, we're looking for CDB, which is marked theta. And you can also remember the rule we had yesterday. Okay, remember the rule we did yesterday and on the same segments? Looks like AD divides also this circle into two segments, which are two semicircles right now. And then we can also tell that whatever ABD is, ACD should be that too. That's the angle that B and C should be equal. And now we know that we don't have to be given any figure to know what the figures are, because we know that if the segment you're thinking of is a semicircle and the angle formed on the circumference from the chords joining the two ends of the diameter will be 90 degrees. So we know that C and D are 90 degrees each. You see, I just matched two rules. The other rule helped me find the value, but the other rule established that they're going to be equal. Now, if we look at the angle ACD, which contains the triangle that we're looking for theta in, then we'll see that C is 90 degrees. And if C is 90 degrees, let's look at triangle CED, the small triangle formed there, CED, where the theta is. Now, if we have C as 90, and we see that the point E there of triangle CED should be 48 degrees, that's vertically opposite angles to the E on DEA. So we have that C is 90 degrees, E is 48 degrees, and if we add 90 with 48, we have 138. Sum of angles in a triangle, the triangle ECD right now, should be 180 degrees. So we say 180 minus 138. Then we find that theta is 42 degrees. In solving circle theorem, you have to have a basic knowledge of angles. If you remember from angles, you will see that the 48 degree in triangle ABE is vertically opposite to the angle E in triangle CED. Vertically opposite angles are equal. So what that 48 that you're seeing in this diagram should also be on the other side. That is like X. The E to the left is 48. To the right of it should also be 48, because those places are vertically opposite angles. So the 48 transfers to that place the E of CED plus the 90 that we know that C is. Because if you look at triangle ACD, you'll see that C is angle formed on a semicircle, and we say for angle formed on a semicircle equals to 90 degrees. So 90 is at C, and CED, the E part, is 48. 90 plus 48 will give you that. So tonight we're going to consider another 2-in-1 theorem. What I'm saying really this time is that we're going to take 2 theorems and consider it once. And generally we're going to just say we're considering the tangents of a circle theorem today. So remember, we've already talked about that when a tangent meets, when an angle is formed between a tangent and the side of an inscribed triangle, that the sides of that angle is going to be opposite the interior angle of that triangle. That's not the case now, because that one was alternate segment theorem. So now we're dealing with tangents of a circle theorem. My God. And let's go straight to it. The first one is okay, let me send you a picture. Now from the pictures I've sent, you can see the first one deals with just a radius and a tangent. That's to say that the angle between a tangent and a radius is 90 degrees. That's just the first one. You see the radius is the blue line. I'm looking at diagram 1. The radius is the blue line. Radius is the line taken from the center of a circle to any point on the circumference. While the tangent is the pink line. Tangent is a line, a straight line, that touches the circumference of a circle at one point. So the pink line is a straight line and touches the circle's circumference at the point A. So now we have a radius and a tangent. And we say that if a radius meets a tangent, it's going to form an angle 90 degrees between them. Now on the right hand side is the second tangent of a circle theorem. That one says that if, two tangents, like you can see tangents on the purple tangent, diagram 2 now, and not the pink tangent, the purple tangent and the pink tangent, if two tangents meet at the same point, the point A is where they meet. So the purple tangent and the pink tangent meet at point A. So if two tangents meet at the same point, then those two tangents are of equal length. Now I want you to pay close attention. When we say they are of equal length, we mean, remember I said a tangent touches the circumference of a circle at a point. That point where it touches the circumference of the circle is where our counting of measuring of the length starts. So if you see the purple tangent touch the circle's circumference at point B, and the pink tangent touched the circle's circumference at point D, when that happened, and then the two tangents meets at point A. If you look at the pink tangent, from point D to A will have the same length as from point B to A in the purple tangent. That's what the rule in diagram 2 says. That when tangents meet at the same point, those tangents are going to be of equal length. Okay? Now I want you to still consider this diagram 2. The diagram 2. Look at it and pay attention. As in diagram 2, you have two tangents that meet the circle at two different points, B and D. And then the two tangents intersect at point A. The two tangents meet at point A. Now, if point B and D, you see B and D, just look at point B and point D on the diagram 2. If we draw a chord to link D and B, as we draw a straight line to link D and B, then AB and AD will be of the same length. Now, we've already known that. But I now want you to look at the chord you just joined in your mind now. Look away from the left-hand side of the shape, the remaining part of the shape. Just look at from the chord to point A. You'll be seeing a triangle. Now remember that this triangle has two tangents of equal length, which makes the triangle you just imagined now an isosceles triangle. So what I'm trying to say is, if you draw a chord to join points D and B, you formed an isosceles triangle DBA. Now, look away from that right hand side now. Let's look at the left hand side. With the chord you just joined, you will see that you also have a triangle which has two radii, the green and the blue radii, plus the chord you just joined, D and B. So you also have another isosceles triangle at that's CBD, because if a chord, if two radii meets a common chord, then you're going to have an isosceles triangle. So there's a chord at DB, which makes BCD an isosceles triangle, and also makes ADB isosceles triangle. So we have an isosceles triangle formed. Now let's think of, we did not put a chord there, we removed the chord. Then you're going to be seeing that ADCB is a kite. ADCB is a kite without the chord now. I removed the chord that joined DB. So we now form a kite. So what I'm saying is that this diagram too can yield an isosceles triangle and a kite. Alright? Now in this question we are asked to find BAD. BAD, that's the angle between the tangent and the side of that triangle. Now I just caused a problem. Now I don't want you to rush and be in a hurry and say, oh, when an angle is formed between a tangent and the side of an inscribed triangle, then the side of that angle is equal to the opposite interior angle of that triangle. Yes, it is true. But I want you to stick to the rule we are doing today, because it provides you with an alternative method or alternative way of solving this problem, in case that's the one you would understand better. So we are looking at the angle today that says, the theorem today that says that a radius meets a tangent at 90 degrees. So we are looking at this question and we're looking at radius OA meeting tangent DE at 90 degrees. So we say OAD equals to 90 degrees. Now, we remember that, okay, so we have a triangle that has 52 degrees. So if we find the remaining two, if we find even one other angle in that triangle, we can find the third angle, which is at A, and then, okay, so what I'm saying is, we remember from yesterday's rule that angle formed a semicircle, that's a triangle ABC, that point B is 90 degrees. And we already have point C to be 52 degrees. So we say 90 plus 52, and it gives us 142. So to find BAO or BAC, the angle at A, we'll say 180 minus 142, and we have 38 degrees. So we have that the A of ABC is 38 degrees. And remember that OAD is 90 degrees. So we say 90 minus 38 degrees, and we have that theta is 52 degrees. It's the same as when you would just look at it and say theta is 52 from the rule of alternate segment theorem. Now example 2 is still dealing with the first part of the two theories we are dealing with today. That's radius meeting a tangent. Again, don't be fast to say theta is 48 degrees, because I know what is on Treasure's mind right now. You're thinking, why do we need to stress ourselves when we can easily say theta is equal to 48 degrees? When that comes up your mind, tell yourself, shut up and listen. Okay? Now, we are going to look at chord CB. Chord CB. So chord CB makes or divides the circle into two segments. So we can see that triangle CDB should be equal to triangle CAB. So the 48 at D should be the same in A. So A is 48 degrees. And now look away from that and look at diameter AC. Diameter AC forms an angle in a semicircle at B. So B is 90 degrees. Remember, angles in a semicircle is 90 degrees. So we have 48 at A, 90 at B. So we can find this point C by saying 90 plus 48. That's 138. So if we have 138, we say 180 minus 138 degrees. And we have that point C of ABC is 42 degrees. Now, if that point is 42 degrees, remember, OC is a radius that meets EF, a tangent. So that means OCF is 90 degrees. So we have the point C as 42. So to find the theta, we say 90 minus 42, which gives us 48 degrees. Okay? Now, I want you to pay good attention in this one. This one deals with the second part of the two theories we combined. Now, we're asked to find DFB. DFB, you can find that place theta just down here. Now, to find that, we're going to need the rule we did today. But I want you to be able to identify where would give you the answer easily. Look at the shape OCDB. That is the main shape we need, because if we find the B part of OCDB, then we can easily find theta. Alright, so that's what I mean is that OB is a radius, so which makes, and FA is a tangent, so which makes OBF 90 degrees. So if we find the B part of OCDB, if we find a value for that place, then we can say 90 minus that value and we find theta. So everything we're going to calculate now is just to help us find a value for B of OCDB. So let's go. We look at the 72 degrees at the center. At least you have 72 degrees there. Now we should complete that whole center of the circle 72 degree part to be 72 and another 72, but you need something to back up, and you need to be sure that that is 72. So let's find a way to be sure. You are sure that CA and BA are of equal length, right? Okay, so that means if we draw a chord to chord C and B, then ACB, triangle ACB, is an isosceles triangle, which, remember, as I explained, triangle OBC is also isosceles. If triangle OBC is isosceles, and then remember radius OC and OB form the two chords, two arms that meet the chord CB, that makes the O part of triangle, the isosceles triangle OBC OCB 90. That makes it 144 degrees. That's to say, because since it's isosceles, then this line OA is dividing that triangle into two equal parts. So if it's dividing into two equal parts, then 72 should also be on the other side. So I said 72 plus 72 to give me 144. So I have 144 at the center. And if I have 144 there, then we can find D of OCDB. And we say that D is 72 because we say angle at center, angle at the circumference is half the angle at the center. So 144 divided by 2 will give us 72. So now we found the D part of OCDB. Now look at the C part of the angle C of OCDB. You have 80 between the tangent and the side of the triangle. And then remember in our when we introduce this topic, line CA, line AE, A is a tangent, and OC is a radius. So the radius OC is meeting tangent AE at 90 degrees. So if that is so, then we're saying that OCA is 90 degrees. Are you saying that with me? So OCA is 90 degrees. And then we have that DCE is 80 degrees. 90 plus 80 is 170. An angle on a straight line should be 180. That makes C 10 degrees. 10 degrees. So we found the C part of OCDB as 10 degrees, and we found the D to be 72 degrees. What is remaining is for us to find out B now. So we add the 10 to 72, and we have 82. And then let's find O, the O part now. The O part will have to be, remember, the down part of O, the lower part of O, the part that is in COBA is 144. So we can say 360 minus 144. We have 216 for the O part. Okay, so the O part of OCDB is 216. So we have 216 for O part, 10 for C part, 72 for D part. So we add all those together, 216 plus 10 plus 72, and we have 298. Okay, then we're going to say 360 degrees minus 298, and it will give us 62 degrees. So we have now that the B part of OCDB is 62 degrees. And so we can say, remember that OBF is 90 degrees. So we say 90 minus 62. And we have that theta is 28 degrees. It's a long explanation, so you can pause and listen again till you understand. All right. Remember that a chord is a straight line that connects 2 points on the circumference of a circle. From this picture I sent, the chord is the blue line. You can see the pink line does not touch the circumference on 2 points. It just touches on 1 point. It started from the center. So the line that starts from the center to the circumference is a radius. So the pink line is a radius. But the blue line touches the circumference at 2 points, A and B. So the blue line is a chord. That's the chord we're considering today. All right. Again, I'll remind you that the longest chord is the diameter. So you can keep adjusting this chord until you get to the middle, as long as it still touches the circumference on 2 sides. And you can adjust it to anywhere you want. All right, now you see the pink line is a radius from the center to the circumference, but passes through the chord AB. It passes through the chord in such a way that it forms a perpendicular. And what's a perpendicular? When a vertical line, vertical is upright, standing straight like you are standing, if you are standing. When a vertical line meets a horizontal line, then a perpendicular is formed. If you can rotate your screen so that the blue line is your horizontal line, then you will see that CE, the radius, meets that chord AB to form 90 degrees on it. So CE and is perpendicular to BA. So a perpendicular is formed. Now when you have such case, that's when you have a perpendicular from the center of the circle. And then to cut across, to cut or bisect a chord, then that perpendicular is going to divide that chord into two equal parts. I'll put it in simpler terms. Line AB is our chord. Line CE is our perpendicular. I've explained what perpendicular is. If a perpendicular like this CE meets a chord, then it's going to divide that chord into two equal parts. That's to say, from B to D, which is the middle of the chord, is going to be equal in length with from D to A. That's why both of them are marked as X. So the rule is that the perpendicular from the center of a circle to a chord bisects the chord. Remember I said bisect means to divide into two equal parts. So the perpendicular from the center of a circle, that's CE, to a chord, that's AB, bisects the chord, that splits the chord into two equal parts, or divide the chord into two equal parts. Hope you understand the rule. So you see that it's not just that, it's not that the arrangement will always be in the same way like I placed the first diagram. It can rotate, but what you're looking out for this theorem is you're looking at the chord BAB, or it could be labeled anyhow. We'll see when we start solving. When you look at that chord, look and see if there is a line from the center of the circle that cuts that chord. If that happens, then you've activated this rule. And what you should know is that the radius that formed the 90 degree to the chord has successfully divided that chord into two equal parts. Now, in this theorem, we're not going to be looking for angles, though we'll need angles to find what we want. In this theorem, we're going to be looking for the length of the arc. All right, so we're going to be looking for the point we marked X in the former diagram. That's AD or BD or whatever it is. But we are going to find length now, not angle. Okay. All right. So we see here that we're asked to find line BC. Line BC is marked X. That's this chord we're seeing by the left side of the circle. Now, what do we need to find that? First of all, let's see what we would see to know that there is this rule we are discussing today. We see the chord AB is there, and then a radius from the center O cuts that cross that chord, and then forms a 90 degree, so that we know that BE should be equal to AE. That is, the 5 cm that is on AE should also be on BE, because the line BA has been cut into two equal parts. So if one part is 5 cm, then the other part should be 5 cm. So we're going to we're looking at triangle BCE. So we've discovered that there is 5 cm on BE. So the base of that triangle BCE is found as 5 cm. Then you look at the angle, or the chord CA. If we put a chord at CA, then we discover that triangle CBA and triangle CDA are on the same segment. So that means the 71 on CDA should also be on CBA. So we found angle 71 for the B of triangle BCE, and we found 5 cm for the base of that triangle, that's BE, and then X is on the other side. So we have all it needs to solve for X using Pythagoras theorem or trigonometry. So we have the angle given to us. We don't have the opposite. We have hypotenuse and adjacent. That means we're invoking cos theta. So if we use cos theta to solve, that's cos 71. Remember, cos is adjacent over hypotenuse. So if we use it to solve, we will discover that X will be 15.4 cm. You can solve that and confirm, but mine is to make sure you understand how to find X. All right, here we're asked to find AE. It's marked X there. Look up left. AE. Now, we also see the rule come to play here. Chord AC is the chord, and OE or OB, the radius OB, is the perpendicular. So it cuts the chord into two equal parts, and forms a 90 degree. So we have X on AE. We know that means that EC is X2. All right. So if EC is X2, we know that if we find EC, then we found X. Now we're going to transfer everything and use the triangle DEC to find EC, because we know if we find EC, then we found X, right? So let's see. We have angle 35, and EC is our X now. Understand that? So angle 35 is there, then the opposite is EC, opposite is X, and then the hypotenuse is 8. What rule do you think comes in play there? You have opposite and hypotenuse. That's SOH. Treasure stop. So SOH, sine equals to opposite all over hypotenuse. So if you say sine 35 degree equals to x all over 8 and solve, you will discover that x is 4.6 cm. I know that you found x for EC, 4.6 cm, and because of that, because EC is the same as AE, then the x at AE, which is where we are asked to find, is 4.6 cm. Do that what I want to say. Now in this case, we are asked to find BE, line BE. Where's BE? Okay, BE is marked X as your right center to the center to the right. Okay, now we're going to use that 77 to unlock something. The X we are looking for is in the triangle AEB. AEB. Alright? Now we see that FG is a tangent at B, and a radius meets that tangent, so that means there's 90 degrees between. That's OBF is 90 degrees. And if we have 77 as the angle between the tangent and the side of that triangle, then 90 minus 77 will give us the angle B of AEB, which is 13 degrees. So we found 13 degrees to be the angle inside the triangle at B of triangle AEB. Then X is the base of the triangle. Remember, the 90 degrees on AEB. The angle E, there is 90 degrees. So we have X as the base. We have an angle 13 degrees at B. Now, remember that AC is a chord, and OD is a radius that cuts that chord. So it will form a 90 degree and divide the chord into two equal parts. So if that radius OD has divided the chord AC into two equal parts, then the 12 cm on the one part of that chord should be also transferred to the other part. That means AE is also 12 cm. So now we have what we need. We have 12 cm for the perpendicular part of the triangle. We have X on the base part of the triangle, and then we have our angle 13 degrees. So because the angle is at B, then AE becomes the opposite, and X is the adjacent. Looks like we've activated tan theta, or opposite adjacent. Okay, so we're dealing with tan 13 equals to 12 over x. So if we solve that, x will be equal to 12 over tan 13. Yeah, x will be equal to 12 over tan 13, as if you reduce that well. So you will have that x, when you solve, will give you 51.9, which is 52 cm. Okay, the simplest way to solve this is to see in the question, the information given to you is that AB is parallel to CD. Now I want you to look to how does that help us. Look at the shape of the line AB and BO. Go that way. AB to O. You see, AB is diagonal, O is horizontal. So you see the same thing happen in OC and CD. DC is diagonal, CO is horizontal. That's why that's what those arrows are for, because they are the same. AB is parallel to CD. Because of that, the 40 in angle B, that's ABO, should also be in angle C, that's OCD. So if we transfer that 40 to that place, and now we see again two radii meeting a common chord, that means triangle OCD is isosceles. If we put 40 at C, then 40 should be at D of OCD too. Now, but we are looking for ODE, and ODE is in triangle CDE. So we have that the C part, that's the angle C, is 40. Now, if we look at CDE, CDE is 90 degrees. But we already know that CDO is 40. So we say 90 minus 40, and we have 50 degrees for ODE. As simple as that. Let's first find MNQ. MNQ is the angle N here of this isosceles triangle. Alright, so M, the whole of M is 50 degrees, and its opposite P. It's opposite P, so P should be 180 minus 50, which is 130. Now, so P is 130, the whole of P. But if you look at MPQ, MPQ is 90 degrees, so we say 130 minus 90 degrees, we have that the P of, that's MPN, the P of the isosceles triangle here, down here, would be 40 degrees. So if this is 40 degrees, then the other side, the M part of this triangle, MNP, should also be 40 degrees, which makes the isosceles triangle, that's OMP, the M part 10 degrees, because you will say 50 minus 40, and you have 10 degrees there. So I'm saying we have 40 degrees for PMN, we also have 40 degrees for MPN, because these are base angles of an isosceles triangle, they're equal. How did we find 40? We said that the M is 50 degrees and P is opposite M, so it will be 180 minus 50, which is 130, and that MPQ is 90 degrees. So to find the MPN, we say 90 minus, or 130 minus 90, and we have 40 degrees. So P is 40 degrees, that's MPN, and PMN is also 40 degrees and base angle. So that makes 80. So what's remaining is 100 degrees for N. So MNP is 100 degrees. Now look away from that. Look at OMP, triangle OMP from the center, the OMP. OM is a radius, OP is a radius. So two radii make a chord. So that means that triangle is isosceles. Remember, we found PMO to be 10 degrees. That's 50 minus 40, we're 10 degrees there. So that makes OPM 10 degrees too. So if we have 10 here and 10 here, then that's 20 degrees. If that's 20 degrees, then MOP should be 180 minus 20, which is 160 degrees. And we've gotten MOP. That's one side of the straight line of MOQ. That's 160 degrees. So to get the other side, that's POQ, which we're asked to find. We say 180 minus the 160 of the other side. And we have 20 degrees for POQ. All right?